The power of lightning. For ages, humans would try and explain this awesome force of nature. Early explanations often invoked some form of divine source, like a god or spirit. Thor, Zeus, and countless other gods were often rationalized as the cause of such power. But is divine intervention really the only possible source? Forming an understanding of an invisible force that manifests itself in the form of lightning bolts is not an easy task. But if you've ever walked on a carpet with some wool socks and then touched a light switch, you know about this force: electricity. Now, you might be wondering, what does that have to do with the title of this video? What are we, physically speaking? Well, it has everything to do with it, as it turns out. But to really take a good look at this question, we have to go back to ancient Greece again. The Greeks spent a fair amount of time thinking about things. Their works are notable to us because they're some of the oldest surviving writings around real advancement of human knowledge and thought. One of these guys, Democritus, even theorized that all matter was made up of a single indivisible object, an atom. He thought that if you divided a grain of sand and kept going, eventually you'd reach a point where you couldn't divide it anymore. Thus, the atom was named for indivisible. Democritus thought that everything was composed of atoms. He also stated that between atoms there would lie empty space. He thought that atoms were indestructible and have always been and always will be in motion, and that there are an infinite number of atoms and different kinds of atoms which differ in shape and size. But historians aren't exactly sure what his position on atomic weight was. And part of the reason for that is because it was very difficult for Democritus to prove a theory like his. The Greek scientists or natural philosophers of the time didn't really have very many advanced instruments. They were limited by Bronze Age technology. It would take hundreds of years of technological development to allow humans to understand truly what the theory would imply about reality, about matter, the composition of all things, solid, liquid, or gas. But what about other things like fire, light, or even lightning? Well, if it's physical, then it must follow the laws of physics. The first one to really found scientific thought or being able to understand the phenomena of the universe was none other than Tales of Miletus, credited by many, including Aristotle himself, as being the first true philosopher. Tales of Miletus experimented a great deal with all sorts of things, but unfortunately none of his works seem to have survived. He did have many followers, however, and from what records we do have, we do understand that he was experimenting with this strange phenomenon of electricity as well. He noticed that whenever he would take a substance called amber and rubbed it on some feathers or fur, it would cause some sort of attraction between the fur and the amber. Like Democritus, Tales was limited by the instruments of his time. He couldn't really look further into the amber to really see what was going on. Like the atomic theory, it would take many, many years of scientific thought to really understand the phenomenon of electricity. And how is this connected to the question? Well, just hang on. We'll get there. But first, I think it's important to establish some historical context. In 1455, the Gutenberg press was invented by Johannes Gutenberg. The printing press is very important because it allows for people to write and distribute information at a rate that had never really been matched before. Prior to this, the only real sources of books would be from monks sitting in chapels or cathedrals for hours and hours, copying out line after line of whatever book they had been ordered to recreate. As a result, before this, books were very rare in Europe and across most of the world, in fact. It should be mentioned here, actually, that the Chinese invented a printing press beforehand, but that's for another video. Anyway, after the invention of the printing press, science was able to advance at a much faster rate because people could distribute their information and ideas with much greater ease. A printing press could create hundreds of books in a fraction of the time required for a monk to copy out the same number. For this reason, the printing press is credited as one of the most important inventions in history. Without it, it might have been impossible for Isaac Newton or any of the others of his time to distribute their ideas to the world and for people to really start to consider them and for science to advance. The publication of Newton's works and the foundation of calculus with Leibniz's help is widely considered to be the beginning of the scientific revolution. Beginning with Nicolaus Copernicus and his heliocentric method, and finally culminating in Newton's great unification in the Principia Mathematica, science became a force that would go on to define human civilization. The scientific method had been established and accepted. Even monks and priests began to use it, believing that their god would command them to use their knowledge and intellect for the betterment of humanity. To really come to grips with this strange force called electricity, scientists and scholars would need some way of creating it on demand. For a long time, the only type of electricity that could be harnessed was in the form of static electricity, until finally this device was invented. The Leyden jar, a major development in the study of electricity. These jars were apparently discovered independently by two separate sources. One, a German cleric by the name of Ewald George von Kleist on the 11th of October, 1745, and the other, a Dutch scientist by the name of Peter van Musschenbroek of Leyden. Historians disagree if Musschenbroek himself actually invented the jar, but he's often credited with its discovery. The working theories for electricity for a long time saw it as a type of fluid. This theory was actually founded by one of the American founding fathers, Benjamin Franklin. He thought that electricity could have two possible forms, a positive charge and a negative charge. This was a very important step in the understanding of electricity. Ben Franklin was able to prove his theory of charge conservation with an experiment. He was a major experimenter in early electricity. But in order to do more tests around the mysterious substance, a better source of electricity would need to be developed. One that could provide a constant source of electricity rather than just a quick discharge. Alessandro Volta set his mind to this task. He observed that it was the nature of the metal and the chemicals that seemed to cause the electricity to flow. And so he created a pile of dissimilar metals, separated by paper lined with acid. These voltaic piles, as it turns out, were the first batteries. Up until this point, the only apparatus for experimenting with electricity was the Leyden jar. Now, with a much more constant source of electricity, scientists and experimenters could do much more with electricity and try to figure out its paradoxical nature. One of the most significant of this time is a French scientist by the name of Charles-Augustin de Coulomb. He's a very notable figure in the history of electricity because he formulated the law of electrostatic force, known as Coulomb's law. But what about magnetism? What about magnets? Are they related to electricity at all? Early philosophers didn't think so, but it turns out that they might have more to do with magnets than we thought. William Gilbert, one of the earliest experimenters with electricity, experimented in Elizabeth's court with all sorts of apparatus, and even did some tests on lodestones. Lodestones are just natural magnets, but how do they work? Well, the connection between electricity and magnetism would remain unproven for a long time until the likes of Oersted and Ampere. They discovered that an electrical current would actually produce a magnetic field. How could this be possible? This question would endure for decades. Combining these principles into a unified, complete system of equations would require another great unification, similar to what Isaac Newton had done for the laws of motion. The person who would do this was named James Clerk Maxwell. Maxwell built upon the work of Gauss, Ampere, Poisson, and Faraday to create his system of equations that described the phenomenon of electromagnetism. Maxwell's original form of these equations was much more complicated, and it took the work of another man named Oliver Heaviside. Heaviside simplified Maxwell's equations into the modern form that we use to this very day. The first equation, Gauss's equation, states how electrical charges produce electrical fields. Electric fields radiate outwards from any kind of charge. The second law is Gauss's law for magnetism. This law states that there are no monopoles in nature. This basically means that for every north pole, there is an equal and opposite south pole. Modern physicists have not been able to discover a monopole, a single-sided magnetic field. The third equation, Faraday's law, describes how a changing magnetic field will produce an electric field. The final equation, Ampere's law, was almost complete, but Maxwell needed to add something to it to make it a general solution for any electromagnetic problem. He recognized that not just an electrical current would produce a magnetic field, but also any motion of electrical charges or change in electrical field would produce one. So if you took a charged piece of glass and threw it across the room, that would produce a magnetic field. But Maxwell wasn't even finished there. With the synthesis of his equations, he arrived at a strange result. He theorized the existence of a strange phenomenon known as electromagnetic radiation. When he calculated the speed of this, his mind was blown. He discovered that the speed of this field came out to 300 million meters per second. The speed of light. Was this a coincidence? Maxwell didn't think so. For years, scientists would try and understand this strange result, but unfortunately, Maxwell wouldn't live to see the true implication of his discovery. He still believed and was searching for the luminiferous ether, this unknown medium that would somehow carry electromagnetic waves or fluctuations. After the Michelson-Morley experiment disproved its existence, he was left wondering, was he wrong? Maxwell still believed in the existence of the luminiferous ether until the very day he died. The one who would really unlock this secret is a somewhat mythical figure, but this would come a bit later. A few more discoveries would have to be in place first to provide the conditions for it. First, the revival of the old atomic theory by John Dalton, an English chemist. The exact origins for his theory aren't exactly clear to historians, but he did find a method for finding the relative atomic weights. That is, when compared to each other, he found some atoms were heavier than others, and even provided a method for other scientists to do the same. The foundations of Dalton's atomic theory were supplemented by Maxwell and Faraday's studies in electromagnetism. Electricity was understood as a type of energy, and by understanding electricity and magnetism, many new scientific instruments were created to investigate this newly understood phenomenon and how it physically interacts with other substances. The atomic theory would slowly be developed through the hard work of countless scholars of the time. Eventually, the main points of the theory were established. Number 1. Elements were made out of extremely small particles called atoms. Number 2. Atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. Point number 3. Atoms cannot be subdivided, created, or destroyed. Number 4. Atoms of different elements combine in simple whole number ratios to form chemical compounds. Number 5. In chemical reactions, atoms are combined, separated, or rearranged. The experimental proof for Maxwell's theory of electromagnetic radiation came in the form of Heinrich Hertz's radio wave experiments. The real implications of this discovery would not be realized for decades, but as more and more scientists began to experiment with these equations, and with electromagnetism and all sorts of substances in general, these discoveries would change the face of civilization forever. The first step on this journey was made by J.J. Thomson. He conducted many experiments with cathode rays, a new type of experimental apparatus that essentially heated up a small piece of something while inside a glass chamber with all the air sucked out. The cathode ray was a small, glowing emission that radiated from the element as it was heated. Thomson would eventually discover that this emission was a subatomic particle, the electron. Thomson saw that clearly the old atomic model would need to be amended. Clearly, atoms could be subdivided if it was possible to measurably detect the emitted electrons from the superheated element at the end of the glass tube. In his own words, as the cathode rays carry a charge of negative electricity, are deflected by an electrostatic force as if they were negatively electrified, and are acted on by a magnetic force in just the way that in which this force would act on a negatively electrified body moving along the path of these rays. I can see no escape from the conclusion that they are charges of negative electricity carried by particles of matter. Thomson's new atomic theory proposed that the electrons were embedded within all matter, and to keep everything electrically neutral, there would be a positive charge to offset the negative charge of the electrons. Eventually, this would be proven to be incorrect by one of his former students, Ernest Rutherford, hailing from New Zealand. With another experiment, similar to the cathode ray in principle, he proved that the positive charge of atoms was concentrated in the center, what he would name the nucleus. The next discovery in untangling the mysteries of the atom was made by a man from Denmark, Niels Bohr. Bohr worked with Rutherford to further delve into the mystery of the subatomic world. To really tie together all of these discoveries, it would require yet another theory, and in fact, another great unification, similar to what Newton and Maxwell had accomplished. To accomplish this mythical task, it would require a mind just as great. Albert Einstein began studying in physics in his mid-20s, and when he was only 26, he changed the face of science forever. The Annus Mirabilis, Wunderjahr, or Miracle Year. In 1905, Einstein published 4 papers that built upon the scientific community's works and solved the mystery of light. In his paper on the photoelectric effect, Einstein concluded that light could not simply just be a wave. It had to have some other properties to allow it to physically exist. He theorized that all light was a form of Maxwell's electromagnetic radiation, or electromagnetic wave, just of a specific frequency. Light was just an electromagnetic wave, but it seemed to have some other properties as well. To allow it to exist, it seemed to behave as a particle in some circumstances. The electromagnetic particles, or photons, that radiated from the sun traveled to us at the speed of light, flying through the empty vacuum of space, sort of like particles. But as Young's double-slit experiment proved, light could behave as a wave as well. The peculiarity of the subatomic level of nature can be hard to fathom. In Einstein's special relativity paper, he theorized that light was the fastest thing in the universe, and nothing could move faster through space. If something did, it would begin to move slower through time to compensate. But that's a little bit beyond the scope of this video. Thanks to the accomplishments of these scientists, we enjoy some of the most advanced technologies humanity has ever seen. Satellites, the internet, smartphones, the list goes on. The atomic revolution gives an amazing picture of reality. thanks to our understanding of the quantum world. But still we have unanswered questions. Only time and effort will be able to answer them, as those who came before us have shown us. I'd like to thank you for watching. I know this video was pretty long, but I hope you learned something. YouTube itself is an amazing technology, and I'd like to use it, hopefully, to make the world a better place.